Picking up where we left off, we're talking about the more complex gas laws, the combined gas law, and the ideal gas law. So, just based on putting the formulas together from Boyle's, Gay-Lussac, and Charles's law, we get to the combined gas law, where our initial pressure times our initial volume divided by our initial temperature is equal to our second pressure times our second volume divided by our second temperature. Now, the only instances in which you would need this equation is when there are two variables changing. So either you're given two pressures and two volumes, or for another example, two pressures and two temperatures. You could solve for your unknown out of the 6 possible variables. And we'll do an example of that in just a moment. So then with the ideal gas law, this gas law deals with the number of moles involved, and we can predict what volume a gas would have based on how many moles there are and the temperature and the pressure using a constant called the gas law constant. And this constant is represented with the letter R. And R is a number, it's a constant, so it's never going to change. That number is 0.0821, and the unit of this constant is very complex, but the reason it has 4 units in the unit is so that it can cancel with everything else in the equation, giving you the thing that you're looking for. And so the only new variable other than R, which is our constant, is N in this equation, and N represents our number of moles. So if moles are important in the question, then we would want to use the ideal gas law. So let's do the example given here. So it's important to remember that in any of our gas laws, we're going to use Kelvin for our temperature. And you might see the abbreviated STP, which stands for the standard temperature and pressure. So our standard temperature and pressure means that the temperature is 273 and the pressure is 1 atm. Okay, so these are going to be the values we plug in for our temperature and pressure. And we're going to solve for, the question is running off the board, the volume of 3.1, I'll just move it to the next line, 3.1 moles of gas at STP, so our standard temperature and pressure. Okay. So we're going to plug into our equation. We're looking for the volume, so that means our unknown is V, and we know the number of moles, so that's going to be our N. So we have N, T, and P. The only other thing in the equation is R, and since R is a constant, we can just plug it into the equation. So our 1 atm times our unknown volume will be equal to 3.1 mole times our 273 Kelvin times our R, which is 0.0821. And with all of the units in R, we're basically going to end up canceling out our Kelvin and our moles and our ATM, so they become not relevant anymore. Okay, so we can multiply these three numbers, and then to get V by itself, we would have to divide by 1. We know that dividing by 1 will give us the same exact thing we had before. So when we get a calculator, our volume should be, hopefully I did this right, in my calculator the first time, 3.1 times 273 times 0.0821. I have 69, 69 liters, okay? So this would be my volume, and 69 liters is a pretty big value, but remember, we're talking about a gas. Gases take up a lot of space, so it's okay to have a big number for your volume. Alright, so let's do one example with the combined gas law, just so we've covered all our bases. So we have a hot air balloon, and this hot air balloon is pretty big. It takes up 4.3 times 10 to the second liters. So let's remember what that is, our scientific notation. If we were to move that decimal twice, that'd be 430 liters. That's pretty big. And the temperature is 43 degrees Celsius. So we know we're going to have to convert that to Kelvin. Let's just go ahead and do that. 43 plus 273. It's going to give me 316, I believe, Kelvin. Okay, so then the pressure of this balloon is 0.4 atm. So this is our V, our T, and our pressure. Now it undergoes a change of temperature. So the temperature changes to this temperature here. Let's go ahead and change it to Kelvin. 59 plus 273 gives us, I'm just going to add it on my calculator. I don't want to think that hard right now. 59. Okay, 332 Kelvin. This is our temperature 2, because it's after we've changed the temperature. And it says we've also changed our pressure. So this must be our pressure 2. So I'm going to go ahead and put 1s next to our other variables. Now the question is asking us, what is our new volume? So that means V2 is our unknown. So if we plug into our combined gas law, we have P1 over T1 equals P2 V2 over T2. So therefore we have 0.84 times our 430 liters over our initial temperature, which was 316. All of that should be equal to our new pressure, which is 1.12, times our new volume, which we don't know what it is, it's our unknown, and our new temperature over our new temperature, 332. Okay, so now we need to get V2 by itself. We should usually start by moving the thing in the denominator. So I can multiply by this on both sides. So it'll cancel. Oops. Okay. Then I'm going to need to divide by 1.12 because it's multiplied by V2. Okay, so now on the left side I have 332 times 0.84 times 430. All of that divided by 316 times 112. So it's important that you make sure you put the denominator in parentheses so your calculator does not get confused with what you're doing if you're putting it all in at once. Alright, times 0.84 times 430. Okay, so for the numerator I have a huge number, which makes sense, just multiply 3 numbers together. All of that over 316 times 1.12. I've got 353.92. Now if I divide these two numbers, hopefully I wrote them down right. I get 338.8, and this is my volume, right? So this is, the unit must be liters then. And I want us to think about this really quickly. This volume, V2, is smaller than the volume we started with. Now, we increased our temperature a little bit, which normally makes the volume get bigger. But we also dramatically increased the pressure, so the volume must be smaller, because I think the change in pressure is a little bit more significant than our change in temperature. And so that's why we ended up with the value we got here. So this is our final volume. And that is how we use the combined gas law. So if you have any questions about using the equations, you could always come to tutorial. And hopefully this addresses any questions you might have about our gas web assign that's coming up. Okay.